one of the three local speakers. And I've been asked to talk about multiple data sources, missing and biased data. I'm supposed to be, this doesn't work. Okay. I'm supposed to be talking about, the current and future challenges in this area. But I couldn't resist. I was there very quietly in 1993, and I was already doing or presenting some very, very initial results of a piece of work that then appeared a few years later as a discussion paper in the Journal of Royal Statistical Society. And then I was already, in a way, looking at this multiple sources, inference for multiple sources using Bayesian methods. This is where my interest in this area started. I wish this was to work, but I don't know. So for me, the biggest developments since then are increasing appreciation of the need to compare results to data, although,
the USB stick on the front of the stage, USB, and that means the light changes should work.
Oh, this. Here. Anywhere? That'd be useful to have it because otherwise I'll have to. And it doesn't go. Oh, well, yes. Okay, so for me, one of the biggest sort of developments since then it's been the increasing appreciation of the need to compare results to data, although I see there is still an awful lot of debate on this from the discussion that we've had in the last couple of days. That led to a lot of development in statistics and statistical inference in mechanistic models. And then inevitably to consider data from multiple sources. So just as an outline of what I'm going to talk about in the next 20 minutes is giving you some arguments for the use of multiple sources, sort of highlighting, maybe mentioning some of the current challenges, and in particular concentrate on one particular challenge, which is the conflict, and I'll come back to that a bit later on. Use an example to illustrate the concept of conflict and its quantification, and then I'll finish with some final consideration. Okay, so motivation one. I think there's been enough discussion in the audience in the last couple of days about identifiability. And I mean, you must have seen my affiliation at the beginning. It was the MSc Biostatistics unit in Cambridge and the Public Health England. I've worked for quite a few years in a sort of public organization where our work was very, very, very well closely connected with decisions in public health policy. And clearly the need in public health policy decisions is to estimate the prevalence, the incidence, the severity, the evolution of an epidemic. But typically only little information or little direct information, I'll explain what I mean with direct information in a minute, is available in these characteristics. Whereas if we use indirect information, and when I say indirect information, I mean information on functions of this quantity from diverse data sources, maybe we may be able to identify the parameters that define these quantities. And I think there's been some discussion on this in the last couple of days as well. So the first motivation, I would say, is identifiability. The second is increased accuracy and reduce risk of bias in what we are estimating. In principle, and I sort of sort of mark the in principle combination of all available data relevant to the phenomenon we are estimating should lead to more precise estimates and should minimize the risk of bias which is associated to the use of selective information. The problem is this indirect information is often, until recently, has been often ignored or perhaps just only used for validation. So it's not been incorporated in the estimation process. This is, at least in the infectious disease world, is sort of different from what goes on in the statistics and medical statistics, because in those fields, the idea of combining evidence from multiple sources has been established, long established. The Bayesian paradigm is a simple way of combining two sources of evidence, prior knowledge and new evidence given by the experiment. Meta-analysis, for instance, combined studies of the same type. And then in the 90s, there's been this sort of development of confidence profile method in the medical decision making literature, where obviously there was the need to combine information from different sources for different study designs. And since then, I mean, this kind of literature has exploded. And then more recently, under the name of multi-parameter evidence synthesis, these ideas have been applied to the health technology assessment field and in epidemiology. In the infectious disease world, I mean, I've only picked up some examples. This is not exhaustive by any means, and it's only on influenza. In reality, influenza is the one that's got more examples. There are examples, mainly in recent years, of use of data from multiple sources. Now, what do I mean in this talk in general with evidence synthesis? What kind of synthesis am I talking about? Okay, so let's try to see if I can define it in a more mathematical way. So the interest is in the estimation of theta. Theta is sort of parameters got more components, a few components, kappa components, and it could be the parameters of a transmission model, for instance. I'm going to talk this, call this basic parameters. Now, the idea is the estimation of these basic parameters on the basis of a collection n, typically bigger than k, independent data items. So we've got data items. Each of these data items provides either direct information on a single component, theta k or theta, or maybe indirect information on that component, or maybe indirect information on more components. And I'm going to define psi I, a generic, denote with psi I, a generic function of theta. This could be either theta itself or, as I said, a function of one particular component or a function of more components of theta. Then from the independence of the yi, the likelihood is just the product of each component. So this Li is the likelihood contribution of yi to the basic parameter vector theta. Then this is the setup, and the idea is the estimation can be conducted in different ways. Can be, first of all, it's conducted on the basis of both direct and indirect information. But it could be just maximizing the likelihood, or maybe if we like, we can adopt a Bayesian approach, in which case we have to specify some prior distribution for the components we're interested in. Now, of course, most of my work has been in the Bayesian framework, if you like, and O'Neill in 2002 wrote that nice paper on mathematical biosciences, which was sort of promoting the use of Bayesian approaches. but I just want to remind you what the advantages of a Bayesian formulation for estimation is. Well, we can explicitly quantify and incorporate expert information on parameters, as seen in the previous lines. We can easily accumulate indirect data, and I've explained, I think, this. And it's interesting that some of the thing I should be talking about is biased data, but biased data can be seen as informing an indirect function, a function, so it's an indirect data on the parameter of interest. Then we can, fully account for uncertainty final estimates, although this is again controversial. And then it's computationally convenient, because the posterior distribution of any function, the parameter, can be easily derived. I mean, sometimes in a likelihood-based approach, calculating the distribution, even the confidence interval, even the standard error of some particular complicated quantity is quite a challenge. So computationally, this is an advantage. Now, let me just denote a Bayesian synthesis in the way that I've described through a notation which is directly a cyclic graph, and I'm going to spend a minute to explaining this. Okay, this is a way of denoting sort of Bayesian models, and basically they show very clearly, graphically, the dependency between the data and the parameters. In this case, the data here, which are in square nodes, are known, and then the basic parameters are the basic parameter I was telling you about, of which we put priors, they are double circled. Priors which could be independent priors, or could be hierarchical priors, it could be sort of structural priors on top of these parameters. And these are the functions that I was telling you about. So basically the idea is that these sort of arrows represent the relationship between the quantities. These are random quantities, the one in the circle, the square are known quantities, and the solid arrow represent distribution assumptions. So yi is distributing according to some sort of shape or form with parameters which is relating to theta 1, whereas the sort of dashed lines represent some functional relationship. So the idea is that if we knew everything about the basic parameters, everything else would be informed. So if you like, the information goes from top to bottom. If we knew everything, everything will be generated, will be known. In reality, we deal with the inverse problem, which is given the information, the joint information on everything, and in fact on the data, and on the idea is to estimate the parameters, so calculate the posterior distribution of these basic parameters on the basis of all the data. And for instance, then the posterior distribution of this particular parameter will be affected by the information that comes from its prior, from the information from the data, but also to its posterior distribution contributes everything else which is linked to this parameter. So all the priors and the indirect information that is connected to this particular node. Now, this can lead, that was a simple example, very schematic, but this can lead to quite complicated probabilistic models. We are becoming more expert at fitting them, and some of the references, for instance, in the influenza field that I've given before show that, but do we know how to assess them? So again, going back to the problem, how we understand what these models are doing. in particular in the Bayesian model, criticism requires the understanding of the role of the three components, the structure of the model, the prior, and the likelihood. But a key question when we use data from multiple sources becomes only the conflict. So are the various sources of information consistent? Are they given the same kind of inference or result with, around the parameters we're interested in? So to do that, to explain this concept and or conflict and see how we address it or can be addressed, I'm going to use a simple example, very simple example. It's nothing, sort of very fancy. This is an example in a paper in Medical Decision Making 2002, where I think different strategies for screening for HIV in antenatal clinics was studied, and there was either screening, universal screening, or screening of particular high-risk group populations. And within this sort of Bayesian in synthesis, there was there is this epidemiological model, and this epidemiological model which involves notion of risk group of HIV infection and whether the infection has been diagnosed or not. And the idea is that there was a need to estimate these parameters A, B, which represent the proportion of the women in this case in each of these risk group in the general population. Then there was the prevalence, so C, D, E, and then there was a proportion of diagnosed infection in each subgroup. So the basic parameters are A, B, C, D, E, F, G, and H. And there were lots of studies, and some of the studies were giving information, I'm just sort of denoting this as P. So, for instance, this study 1 was giving information directly on the Bayesian parameter. The second study equally was giving direct information on B. The third study, direct information on C, and so on. But then from study 5 onwards, you can see that the information that the study was giving was in terms of a function of all the basic parameters. This is one of those psi that I was telling you earlier. And this is true for all these other studies. So in this case, the graph becomes a bit like this. We have a sort of basic parameter we wanted to estimate. We have the data. In this case, there were very simple data, just binomial data. And the data were informing a function which was either directly the quantity of interest, or maybe, as in P5, was a function of lots and lots of different parameters. It's exactly the kind of setup that I've started with. So a question is, when I estimate any of these parameters, do direct and indirect information agree? So does study 5 and P1, when I estimate A on B, agree, or do they say something different? So, for instance, when I estimate A, this is the kind of direct information that pertains to A, and this is the indirect information that pertains to A. As I said earlier, with reference to generic thing, the information that goes to be combined in the posterior distribution of each of these parameters is actually everything else. Its own prior, its own direct information, but also everything else. So this is just to remind you how the data or the data look like. Now, I just want to point out to this, for instance. This is the posterior distribution of B, that particular parameter, obtained from the direct piece of information, the solid line, and an indirect piece of information. And you can see they are discrepant. So, two questions. How did I, in the first place, compute this posterior distribution from that graph? And second, can we quantify this discrepancy and see whether it's, there is really inconsistent there? So this is takes me back to a more generic graph at the same time that we've been looking at just now. But let's suppose we're interested in estimating or calculating the posterior distribution of a particular parameter theta. And then let's suppose that we can somehow subdivide the information that inform the posterior distribution into parts, into partitions, L1 and L2, which are independent. And I mean, this CP, CH is just you know, the way that we call the likelihood or the parents of, you know, sort of the various components of information that contribute to the estimation of theta. So if we were able to do that, then we could split, and this is the generalization of some work that's been going on in the last few years. We can split the node that we're interested in into bits. One which is informed by the first partition, and the other one which is informed by the other partition. And in one case could be direct information and indirect information. So then the question becomes that of comparing the posterior distribution of the two components of theta, the one informed by the first partition and the other one informed by the second partition. So split theta into theta 1 on the basis of the first partition, in theta 2 on the basis of the second partition. Define somehow the distribution, a quantity which sort of summarizes the difference between these two distributions, and then calculate something like this. C, which is the proportion of the distribution of the difference, the posterior distribution of the difference, the delta, which is less than 0 in this case. So, so the reminiscent of Bayesian p-values. We can do that in our example. For instance, for A, we can split it like that. So we can have the sort of direct information and the indirect information. And for instance, I mean, A is not very interesting, but in this case, the B that we were looking at, this is the distribution of the difference. And then you can see that the C, which is very small, can be quantified. And in some circumstances, this quantity is actually uniformly distributed. So you can actually say something about, you know, the sort of the meaning of the size of this quantity. And then say something about the likelihood of real inconsistency in there. Of course, you can do it at any stage of the graph, so you can actually quantify the contribution to estimation at any point or in any node. So I've actually sort of defined a little bit, quantified a little bit, and the other step is how do we resolve it? Once we identify the existence of a possible serious inconsistency, what do we do? How do we resolve? This is another talk, another time. But basically, the gist, sort of the main points are maybe we misinterpreted the data. Maybe the two data that we were trying to put together were actually misinterpreted. Maybe there were bias, or one of the two sets were actually giving a biased inference, and we didn't know because we didn't realize exactly what the meaning of their information was. Maybe we want to do some bias modeling. So again, in this framework, you can add an element of bias parameters very easily. And these are some of the people that have done a suggestive way of doing that. Or maybe we can exclude the data. By excluding data is always, sort of giving up in a way, because it increases the uncertainty, and then you ignore data that exists. Or maybe we can downweight you can downweight the value of this data, which is another talk, another time. So, summarizing, I don't know whether you needed to be convinced, maybe no, but hopefully I've given you some convincing arguments for the use of multiple sources, data sources. I've mentioned some of the current challenges, and conflict is actually a quite serious one. And I think, even Cecile earlier mentioned some of this. I mean, there are two different kind of are not being estimated, look at two different data sets. Why? And I've suggested a way to tackle it, or to tackle its quantification. But of course, model criticism is much more than just looking at conflict. I mean, one of the other important things to look at in, I'm not very good at this, another important element to look at when you do inference using multiple data sources, what are the drivers of the inference? I mean, we've been talking the last couple of days again about the sort of relation with policymaker or with the ones who actually use this kind of model. They want to know this. They want to know what is driving the inference. Not so much only to understand what is driving, what is contributing to the estimate, but also to understand whether there is a need for collecting any more information. So, and this problem becomes more crucial and harder as the number of data sources increase and the model becomes more complex. So I think this is an increasingly important area of research as new types of data emerge, and we've seen how many, sort of cellular phones and sort of anything, and inference on basic polygons becomes more pressing. So I think this is my final message, and I need to acknowledge Anne and Paul in the audience who've helped me with putting together this talk. Thank you. Everyone wants to go for lunch. Julia.
Thank you, it was a nice talk. You mentioned at the start we're going to assume that the data sources are independent, right? But we can think of examples, for example, with the, say, global influenza, sequences come from the same place, the epidemiological data might come from the same surveys, the same sources, same countries. So the data aren't properly independent. Are there ways of dealing with that?
Maybe the data are conditionally independent. These are all data that are informing the same parameters. Yes, a good question. Yes. Sometimes we have looked at data maybe coming from similar sources, but looking at different kind of aspects. So you can imagine they could be independent, but all in all, maybe they're not. So there is an extra thing to consider. Yes. Then it becomes much more complicated.
Well, maybe you can add one level to your hierarchical model. You should just explain how the data gave two different outputs.
Well, there is a scope for enormous elaboration of that kind of little simple thing. You can add levels to create hierarchical structures. You can add time, obviously, which is, I didn't put in there for simplicity, but that is one of the things. So I think there is an awful lot that can be introduced in that. Well, you just need to think a little bit more carefully, I think. And it becomes a little bit more complicated, but this kind of approach is quite flexible. And sort of it lends itself to formulating quite complicated models. Of course, what is it? This cannot be addressed with wind banks. What is it? So the wind banks did exist in the 90s, but here you are. But you're not going to be able to. Most of these things, the more complicated things. I mean, the one I've shown you can solve it with wind banks, but usually you have to write your own code if it's sort of substantive, being complicated model.
Okay, that's great. Thank you very much.